Hi, my name is Jungsung Park, and in this presentation, I'd like to talk about using V-Net with conditional random field for brain extraction. So what is brain extraction? It's a method also called frequently as skull stripping. It's removing the non-brain part from an MRI scan, which is often done with T1 modalities because whatever type of MRI scan you acquire, you usually acquire the T1 scan with it. And brain extractions can sound easy, however, there are many things to consider, along with artifacts or noise that the MRI scan frequently has. So this is an example of what skull stripping brain extraction would do. Um, you can see this would be the input T1 modality, and this would be a good output, and this would be a bad output. You can see the bad output from the model would be removing this part of the brain, probably because there's a blank region here, and then it loses some details around here. Yeah, so this is the kind of results that we would want to have. And of course, since a brain image is 3D, we would want it in 3D. So there are things to consider when designing segmentation algorithms, which brain abstraction and skull stripping, or skull stripping is a segmentation algorithm. First, you have to consider generality. So when you train a model, you train it with your own data set or any public data set, like in brain extraction, there will be Oasis or the Human Connectome project and so on. However, we want the model to work on other data that the model's never seen, like other public data sets or some data acquired from another institution. Any data the models never trained on. And also speed. Brain abstraction is the pre-processing step. You would have tons of other analysis you would want to do on the brain imaging data after this pre-processing. So you wouldn't want skull stripping to be a bottleneck in whatever sequence of methods you want to run the data on. And also, you wouldn't want over or under segmentation. So over segmentation would mean you are including parts of the skull or CSF as brain, and under segmentation would be losing some of the brain parts like the image before. And this can interfere with future analysis you want to run on the data. And also consistency of the label. So we know that the brain is one large chunk. It's all connected to each other together. So we wouldn't see any small brain chunks floating around or some kind of hole in the brain, right? So we would need that consistency in the label when we're doing segmentation. So this is our overall proposed model, and I'll discuss what each of these two parts mean. So first, to discuss the deep learning part, convolutional neural we have to first know the convolutional neural networks. As many of you know, convolutional neural networks is the most used deep learning method in images, currently in images. This is the first model called AlexNet that was used first in ImageNet classification. So this is one of the very first model, convolutional layer model that was used for images. And you can see on a typical deep neural network, it would have a linear relationship between a node from the previous layer to the next layer and then a nonlinear function on it. However, on the convolutional layer, instead of just a linear relation with a Clauser rate, it would have a linear relation with a filter, a kernel. And this filter or kernel does feature extraction from the image. So what we're expecting the model to do is learn those important features of the image that will be important for minimizing our loss, so getting to our goal. In this case would be classification, but we could just change a few layers at the end to easily make it a segmentation task. However, simple convolutional layers might not be important, might not be enough when we're doing medical images. First, because the image data is huge, because we usually work with 3D, and also we don't have that much data like computer vision tasks. If you think of a public data set like MNIST, where we are classifying images of numbers from 0 to 9, they have 50,000 training data. However, public data sets on brain images would be like 1,000, maybe. So we want the model to efficiently learn things. Like we can't expect it to run a large number of epochs on a large number of data and hope it to learn something. So these are two of the main architectures that are used in medical images. The first one is cascaded network. So in cascaded network, what it does, it has a coarse network first, which searches for a patch of the image that is important. And from that important patch of image, it runs a finer network to reach its goal, whether it's segmentation, classification, or anything else. So this is helpful because in some medical images, it could be the case that there's a lot of unnecessary information around, like within the image, and we're maybe trying to segment this little blob here. Then we won't need the whole thing. We will just need this part, like here. And then there's U-Net, which is usually used for segmentation. So U-Net has an autoencoder-like structure. So in autoencoders, I mean type of models that reconstruct an input. So it would first have an input image or input anything, and then it would reduce the dimension of the input to a latent dimension vector, and then it would recreate the input image here. So this reducing step model part, we would call it an encoder, and the recreating step, we would call it a decoder. But I say it's an autoencoder-like structure because, as you can see, instead of reconstructing the input, it's creating an output segmentation map. But this autoencoder-like structure can be important because autoencoders were used so that it could convey important and enough information of the input data in this latent dimension vector, and it should be enough to create the input again, reconstruct the input again without knowing any information from here. Of course, this is a segmentation task, so the model is a bit different. But this autoencoder structure gives it some kind of advantage. And then there's max pooling layers to increase view range. What I mean by this is, if we have a same kernel window size, it will first be looking at this window size of the image, right? However, if we reduce the resolution of the image and keep the kernel window size, now we'll be looking at a larger portion of the image, even if we have the same kernel. So this enables the convolutional layers to learn features of a larger scale. So the more and more we reduce the resolution, the more and more large scales each layer would try to learn. So having this mask pooling layer reduce the resolution every few layers makes the model learn various type of features than just running it through the same resolution for all layers. And there's skip connections for additional information for segmentation. So unlike the autoencoder, it passes down information from each resolution to the decoder, so that if we didn't have the skip connections here, we would have to recreate the segmentation map by just having using the latent dimension vector. However, since we're not like doing an autoencoder task, it might not be enough, and we want the model to use information from every resolution, so every scale of features, right? So this skip connection serves as a bridge of sending those kind of information for the decoder part to create a segmentation map. And U-Net was first made for 2D. However, now there's like things like 3D U-Net and all sorts of varieties of U-Net architectures. There's even architectures where they combine this idea, cascaded idea, with the U-Net, so they have an output segmentation map on every resolution of the decoder layer, and combine those to create a final segmentation map. However, among those varieties, what we choose in our model is V-Net. So V-Net has a similar autoencoder-like structure like U-Net. However, you can see that instead of going down to the latent dimension, it stops at a smaller resolution of the 3D volume. Hence, more of a V shape than a flat U shape at the end. And also, it's important that it uses small convolutional layers to increase view range instead of max pooling. So the way max pooling layer reduces the resolution of the image is by having a window in the image and using only the maximum value within that window. So you could imagine if we have a 2x2 window for the max pooling layer, it would reduce the resolution of the image by half on each axis. However, then if we still imagine a 2x2 window, we are losing we're losing 3/4 of the information, right? So what small convolutional layer would do if it has the same window size and a stride. So what stride does is when we do a convolution of a kernel to image, we would have a convolutional equation on every pixel and its neighboring values, right? However, if we have a stride, we would skip a pixel every time. So in the end, we would have half the pixels on each axis, so we would have a similar effect. However, the convolutional kernel would have weights instead of just hard-coded max pooling. So it would, in theory, convey some information that might be helpful for the model, or the model might want to keep. You can see that the model still has the skip connection, which is important in this type of architecture. And it's also important that the V-Net model was made for, originally optimized and made for 3D, which is one of the reasons that we chose this model. And we also add some changes in the V-Net, like adding some normalization layers and dropout layers. But the important part is that our overall architecture of the deep learning, of the convolutional layer part, is V-Net. However, this V-Net segmentation might not be enough, since when we're talking about brains, we might want finer segmentation, so like more detailed segmentation, and also we would want less errors for future analysis. So there is a method that could kind of fix the small segmentation errors that could happen, which is called the conditional in the field method. So conditional in the field, also called CRF, was originally used for labeling or segmenting sequence data. And people started using it for post-processing step for image segmentation. So what conditional random field does is it creates a marker random field using a graph. And before it was a graph of sequence data, but people thought that we could also create a graph of the image data, right? So we could we could consider each pixel or voxel as a node, and the connection of the pixel or voxel to each other as an edge. So before, when it was first introduced, it would only have edges on its neighboring pixels or voxels. However, now computation power is much better, so people have moved on to something called the dense CRF, which means that we have edges. It's a fully connected network, so we have edges from one pixel or voxel to every other pixel or voxel. However, we will have weights depending on the distance. And the important part when using CRF is that it needs a probability segmentation map. So instead of saying this part should be label C, it should give a soft label like this part has a probability of 0.7 of being labeled C or something. And that can be done by a convolutional neural network, because deep learning as an output of a segmentation map, it usually runs a softmax at the end, which gives a probability distribution of being a certain label. So before it was used with deep learning, what it would do is first have an approximation, a mean field approximation probability distribution of the real probability distribution they created with an energy function. So the energy function is consisted of two parts. First, the unary potential, which is the original probability segmentation map you would have from another method. And this would be the bilinear part where they use information from its neighboring or its connected pixel or voxel. And this what mean field approximation does is, even if it's not true, it assumes independency between a certain label of one pixel, of one pixel being a certain label and another pixel being another certain label. So and then it aims to, through iterating certain equations, what it aims to do is it reduces the KL divergence, which is the similarity between two probability distribution of this approximated one and the real probability distribution. And if we optimize it through that, in the end we would be close to optimizing to a point where it's also maximizing the original probability distribution. So I won't go into detail of how how mean field approximation actually works. The important part is that there's using the connected pixel voxels information part. The first paper proposed doing an appearance kernel for two kernels to do that. One is the appearance kernel, where it uses the positional information, so positional difference between the connected pixel voxel, and the difference in intensity. And the smoothness kernel, which only uses the difference in position. And you can see that it has different weights, which here in this algorithm has to be hard-coded. And also it has a compatibility transform. In this case, uses a POTS model where every neighboring pixel voxel is connected, and its edge weight is 1, and everything is 0, so not connected. And you can see that it calculates a new Q value, so a new approximate probability distribution, and it iterates the same thing until convergence. So this iterating part was the important part when another team created a CRF as RNN. So RNN here means a recurrent neural network, which uses sequential or temporal information. So what they're saying is, since we're iterating iterating and updating the same thing, we can treat it as a recurrent neural network and take each step of the iteration and consider it as a temporal or sequential information. This means that we can add this whole mean field approximation part to a deep learning network. So that also helps us by the fact that instead of using hard-coded values for these parameters, now we can make the model actually train and optimize the parameters that is best for the model. And also this is easier because this message passing step, which is the extracting the neighboring information step, can be done as a convolutional layer. So it makes the model much faster and easier on training. So the advantages of using CRF is that it can serve as a refinement step to fix the segmentation. It uses this neighboring information to say, oh yeah, maybe the prediction of this label that you have from your previous method might be wrong. It also removes segmentation affected by noise that could be in the T1 modality, structural MRI, and it adapts the segmentation to a more complicated structure, which is also important when we're doing structural MRI and when we're doing brain imaging. So here you can see an example of what they did on a computer vision task. And you can see that it removes this label holes here. And then it has it shows a more complex segmentation. And not just on the bike, but on other parts too. So our proposed model is using the input T1 modality, the 3D volume, running it through a V-Net to get an initial segmentation result like this, which is good enough, but we refine it by using a CRF SRNN layer to remove some wrong segmentations and make it finer. So this part, you can see that it slightly has some segmentation of the CSF, which CRF SRNN layer can remove. So the predicted results would be that since we use various public data sets to train the model, and however, those public data sets, ground truths are usually machine learning algorithms outputs, so it might have its errors from its own priors of the model, and CRF could be a refinement step that fixes those errors from the priors of the machine learning models. Also, deep learning tends to be really fast, and adding a CRF RNN layer after the V-Net is just adding a few layers, so the speed won't be a concern as long as you train the model in advance. Also, since CRF solves small segmentation errors, it would solve over-under segmentation and consistency problems. So this is the result from just using V-Net and V-Net with CRF, and the green part is just using the V-Net architecture. The red part here would be the V-Net plus CRF, and the yellow part is the overlap. You can see it removes these small chunks that could be flying around the brain and some wrongly segmented parts. And it gives a finer segmentation. It fixes a few things here and it removes some parts that's not supposed to be the brain, but comes from a part of the maybe like another machine learning algorithm that wants the brain to be a more atlas shape and not have some holes like this. Yeah. And so this is another result where we compare V-Net plus CRF with other methods. So this is the famous BET method, which a lot of people use on brain segmentation, brain extraction. And you can see it has a huge error here. And deep brain is a pretty decent deep learning method that people use to do brain extraction. And you can see that it removes those big errors, so it does a pretty decent job, but it loses some finer details in the segmentation, like in these parts. And V-Net plus CRF catches those finer segmentation in the end. Unfortunately, we don't have a public code yet. However, hopefully we'll have the code ready for you to try soon. So thank you for listening to the presentation, and if you guys have any questions, I'll see you at the Q&A session. Thank you.